Well, we were interrupted by some alarm, but then I do realize when I compute this, when I plug in the y equals x cubed, I think I made a mistake of copying on the wrong thing. Let's correct it, and then we continue our calculation. Now we can see why we need to have this x cubed dx because of this, right? So du 1 over d 1 over 4 times du equals x cubed um, times dx, obviously. So we can find the antiderivative. Well, maybe you should do it here. So antiderivative for x e to the x to the 4 times x cubed dx. So this is supposed to be um, uh, e to the u du times 1 over 4. So the antiderivative is indeed 1 over 4 e to the u, which is 1 over 4 e to the x to the 4. So this is what we should have. And now we just using this antiderivative, right? So we have 1 over 4 e to the x to the 4, and x is evaluated at 0, and cubic root of 2. So so we get 1 over 4 e to the cubic root of 2 to the 4 minus e to the 0. So this is what we have. We can simplify a little bit, but not too much, because this cubic root of 2 is 2 to the power of 1/3. This is 4 over, well, 2. This is 2 to the power 4 over 3 minus 1. So that's pretty much what we can get. Okay. And this tells us, if we review the process, the original iterated integral set it up for a double integral in this domain is really hard to integrate because of the integrand, right? So the trick we played here is to realize this integrand has nothing to do with this y variable. So we try to integrate along um, on that variable y first. And what we did is looking at the same domain, but treated this domain as a type 1 region so that we essentially doing this change the order of the integration. Okay, so this is one technique. There are other important examples we want to go over. For example, how about we just compute surface of the portion on graph of function z equals 10 minus 2x squared minus y squared. Oh, yeah, 2 times y squared. That lies above the z-axis. Sorry, above the xy plane. How do we do it? For those kind of questions, it's very helpful if you have some idea of the surface, how the surface look like. And but also it is also very important to recall what is the right formula we need to use. Obviously, the area could be computed by this, but then you got to really know what is this differential surface area and how do we determine a particular portion of the surface as here. Okay, so for this question, we do realize the parameterization is a graph of function z equals 10 minus 2x squared minus 2y squared. So the parameterization will be depending on x and y, if you realize. Okay, and the parameterization written in the vector form should be this. And the normal vector should be r sub x cross r sub y. But because we just need the surface area, we do not really need to compute that. What we really need to compute is differential of the surface area is indeed the length of this normal vector times x dy, and particularly the length of normal vector is already given. So if you say this is f of x, y, or if you just use the z variable, it is partial z partial x squared plus partial z partial y squared plus 1 times dx dy. Okay, and this is telling us the first important piece we need to figure out. But there is another important piece we need to figure out, which is how do we specify the parameter xy such that we got the domain. Okay, so let's see. The surface is on the graph of this and also lies above the xy plane. So we need intersect z equals 10 minus 2x squared minus 2x squared with xy plane. Here, this is knowledge. You should remember with the xy plane. How do we use Cartesian coordinates to represent it? It is z equals 0, right? How do we intersect this surface and this surface? We just equal them together. We just make them equal, right? So 10 equals, well, 0 equals 10 minus 2x squared minus 2y squared. So this means x squared plus y squared equals 5. So this is a circle on the xy plane because z equals 0. Okay, those two terms are satisfied simultaneously. So that means the part of the surface S is actually above the disk. So S is above the disk of x squared plus y squared less or equal to 5. Okay, so now with this part 1 and the part 2 discussion, we can find the area from this surface integral for constant 1 like this. The integrand is now not 1 anymore, but the length of this normal vector, which is partial z partial x. What is partial z partial x? I think partial z partial x. Note. Partial z partial x is negative 4x. Partial z partial y is negative 4y, right? So we have negative 4x squared plus negative 4y squared, and then plus 1 dx dy. So this is what we need to compute. It's not so bad. So if we simplify, we should see this is 16x squared plus 16y squared. So we put them together. This is what we need to compute. Well, over here, obviously, this is only involving the calculation of a double integral. So we can choose a better method to compute it. For example, we can introduce the so-called the polar coordinates, right? So obviously, this is this disk x squared plus y squared less or equal to 5 is disk theta r. So theta is between 0 and 2 pi for the disk, and r is between 0 and the square root of 5. So theta is between 0 and 2 pi, r is between 0 and the square root of 5, and the integrand has to be replaced by the polar coordinate, which is 16 times. Remember, in the polar, x squared plus y squared is indeed r squared plus 1. And then the dx dy is becoming what? So x squared plus y squared equals r squared. Dx dy equals r times dr d theta. So we have to have r times dr d theta for our calculation. Okay, so this is what we have. Theta is between 0 and 2 pi, and we can find an antiderivative. RDR is what? Well, I guess we have to use U sub again. So U is 16 R squared plus 1. So DU equals 32 RDR. So RDR equals DU over 32, and this is becoming becoming, I think, square root of u, and you can find the antiderivative of that and then finish the calculation. Well, there are some steps. It's not the important part for our discussion. I'm just going to list the result for you. And what you should remember is that you can compute this to very end. Okay. So now let's look at another example, which is also relevant and a little bit challenging. So here, use the spherical coordinate to evaluate this triple integral x squared plus y squared plus z squared dv, where this solid E is the region bounded by a ball centered at the origin with a radius phi, and z equals. So how do we do that? Remember, the only trick I want to emphasize here is that dv, which could be dy, dx, dz, And if you want to convert it into spherical coordinates, you have to do this. This is what I'm trying to emphasize. Right? Also remember, x squared plus y squared plus z squared equals rho squared, and the surface z equals the conversion for the spherical coordinates. We find that z is rho times cosine phi. All right. So this so z equals square root x squared y squared is equivalent um to what? So this is here, but the right hand side is what? The right hand side is indeed rho times sine phi cosine theta squared plus rho times sine phi sine theta squared. Okay, you can see after you square them and use the trig identity, what you should see on the right hand side is u times sine phi. And remember, the azimuthal angle phi is always between 0 and pi, so this is always positive. And on the left, you have rho cosine phi. So we cancel the rho, and we can see y equals tangent phi. So phi equals pi over 4 represent this cone. Okay, so our domain is between this sphere and this cone. So the upper limit for the phi angle is pi over 4. Okay, so the integral we're setting up here is indeed, let me call it I. So I is what? Theta is between 0 and 2 pi, and phi is between 0 and pi over 4, and rho is between 0 and 5 because of this radius of the ball we are looking at. All right, and the integrand, there is indeed integrand. This is indeed rho squared. Okay, so we have rho squared times, now this dv is rho squared sine phi d rho d phi d theta. So this is the integral we need to set up and evaluate. I think this is pretty straightforward. Okay, but let's just pause, and then we'll discuss examples related to the first half of the course.